tower, again from University of Texas, and you find the edges, and you might just want to see whether or not you might be in the state legislature and you want to make sure the tower at the University of Texas is not leaning to the left. That's a joke for some of you. But we're going to assume for now that finding lines is something we want to do. So you might be wondering, well, wait a minute, we just spent a long time learning about how to find edges. Aren't we done? Can't we just find the edges? Well, if that were true, I wouldn't be standing here. So let's talk about the difficulty of line finding. So here's that same University of Texas tower, again courtesy of Kristen Grumman, and we've run an edge operator. And what I've done here is I've pulled up a part of it just so we can talk about some of the phenomena. So problem number one is that there's lots of points here that have nothing to do with the lines. Okay? So all these little edge points down here, these have nothing to do with the lines, so we have to be able to deal with them efficiently and rapidly. Second, only parts of the lines are actually detected. So for example, here you can see that there's this big gap in the line, even though what we'd really like to do is say that we found the entire line. And finally, there's noise and corruption actually where we do find the edge. So over here you'll notice that in these lines across here, there's all this stuff that doesn't exactly lie on the line. You can see the pixels are jumping around here as well. So we have to be able to go from these noisy measurements of where the edges are in order to find the actual lines.
All right, let's try to build some intuition about how to go from edges to lines. Remember that edge images are just collections of pixels. Pixels like these where possible lines could be found. How many lines can you identify in this image? So you could identify lines in different ways. For instance, this could be a short segment, a longer segment to the right-hand side, and a diagonal cutting across. Now this is a consistent set of line segments, which almost accounts for all of the edge points. But there are other possibilities. For instance, this long segment going right through, and two shorter segments on either side. There's no single correct answer to this question. If you entered 2, 3, or 4, we would accept it as correct. Hopefully this will give you an idea how finding line segments in an image is not a trivial task. This is especially true if you don't have any additional context and are looking at edge pixels individually.
As I said before, it's not feasible to check every possible line, even with a really, really fast computer. What we have to do instead is somehow allow the data to speak to us, allow the data to decide where the lines are. And because this is democracy, what are we going to do? Well, we're going to do something called voting. So voting is a general technique where we let the features vote for all the models that are compatible with it. And the way it works is pretty straightforward. We cycle through all the features. Now, today for mostly features, what I'm going to mean is little edge points. All right? And each edge point is going to cast a vote for the model parameters or the different sets of model parameters that it's happy with or consistent with. And when we're all done, we look for the model parameters that receive a lot of votes. And those are the parameter models that we're going to instantiate. Why does voting work? Well, voting works for the same reason that Mickey Mouse, Donald Duck, and Lara Croft are never elected governor of California. Angelina Jolie, maybe, but not Lara Croft. You see, what happens is, in every election, there are people, there could be millions of people who are unhappy with the main candidates, the real candidates, if you will, and they'll write in some silly name, Mickey Mouse or Lara Croft. But even if there are millions of silly votes, as long as they don't all put down the same silly name, then in some sense a real candidate will get elected. And this will work unless Stephen Colbert or somebody like that tries to orchestrate an overthrow. But in general, the idea is that these silly votes are all distributed across sort of the not important candidate. So this works the same way for our computer vision. Noise and clutter features will cast votes too, just like the real features, but typically their votes should be inconsistent with the majority of the good features. Also, another nice thing is, even if part of the circle, say, is occluded and there are no features there to vote for it, because the rest of the circle has gotten a lot of votes, we're able to find the circle. So the example we're going to use today to start with is just on fitting lines. All right? And to fit lines, we're going to have to ask a couple of questions. First of all, given points that belong to a line, what is the line? That is, you know, which line are they picking? How many lines are there? and which points belong to which lines. Now, we're mostly going to focus on the first question for this lecture, and in fact, most of what we'll do, but extensions to what we're talking about make it easy to do questions 2 and 3 as well. So the method that we're going to talk about today is called the Hough transform. And it's a voting technique that can be used to answer all these questions. And the main idea is just that voting principle. Each edge point is going to vote for compatible lines. That is, it's going to vote for any line that would go through it. And then you look for the lines that get many votes. So there might be 2, 3, 4 lines, and you can find all of them. And by the way, if you keep track of which points voted for which lines, you're also able to go back and say which points belong to that line. So I'm going to take you through sort of how this works. And the key to the Hough transform is Hough space. Here we have a line in image space, and you all remember the very first equation you saw of a line somewhere in Mrs. Thompson's or Mrs. McGillicuddy's or whoever your Mrs. Mine was Mr. Zebro, actually. He was also the football coach. I learned algebra from the football coach in junior high school, which is a very strange thing. Anyway, so you remember that the equation of line is y equals m0x plus b0. So what we're going to construct is what's called Hough space, and it's really the Hough parameter space. And in lines, in this representation, we have 2 parameters, m and b. So for this line, y equals m0x plus b0, that's represented at a location in the Hough space at m0, b0. So there it is. There's the point in Hough space. A key idea here is that the line in the image corresponds to a point in Hough space. Okay, you got that? A line in the image corresponds to a point in Hough space. Now we're going to do something a little different. Suppose we only have one point in the image space, and we'll put that point here at x0, y0. Well, what are the equations of the lines that might go through that point? Well, in image space, we know that the line that goes through that point is going to satisfy, for whatever the m and the b are, it's going to satisfy the equation y0 has to equal m x0 plus b. Right? That in order for it to go through the point x0, y0, it has to have an m and b such that this equation holds. Well, with some very simple algebraic rearrangement, that becomes b is equal to minus x0m plus y0. That's the equation of a line in MB space. In fact, it's a line with slope negative x0 and intercept y0. Okay, so the idea here is that a point in image space is a line in Hough space. This is the duality. Well, if we have one point, what happens if we have a second point, x1, y1? Well, that's going to be another line, right? That's going to be a line with b equals minus x1m plus y1. And so now here's the really cool question. What line would be consistent with both points? Well, it has to be the point where these 2 lines in Hough space intersect, because that's the m and b that's consistent with being on a line that goes through x0, y0, and on a line that goes through m1, b1. And this, ladies and gentlemen, boys and girls, and all you interested parties, this is how we're going to find lines from points. So now we have to reduce this to an algorithm. We'll first do it graphically and then actually show the algorithm. So basically, every point gives me a line in Hough space. So what I do is I create a grid. Here it's of m and b. We're going to change that in a minute, which are made up of a set of bins. And every point votes for a line's worth of bins. So it casts a vote in every bin that it goes through. You collect up all the votes, and after every point has voted, and whichever bin has the most votes, that's your line. So this basically, we're going to be casting votes into bins and then finding the bins that have sort of a large number of votes, larger than sort of the average noisy area. Before we implement this in real code and real math, we're going to have to rethink our representation of lines just a bit. You might remember that there were some issues with the MB representation of lines. In particular, for example, a vertical line is really painful, right? Because m is equal to infinity, and in 7th or 8th grade or 9th grade or 12th grade algebra, the notion of having an infinite slope is kind of very painful. All right? So what we want to do is we want to use a more robust representation of lines so that we don't have any sort of bad numerical problems. So what we're going to use is a polar representation for lines. So in our polar representation, this purplish line here is going to be defined by two quantities. One of them is just this distance d. This is the distance of the line to the origin, the perpendicular distance. It's the distance to the closest point on the line to the origin. And the second parameter, so that first parameter is d, and the second parameter is theta, which is just the angle that this perpendicular makes with the x-axis, or if you want, you can have it be the angle that the line makes with the axis. Doesn't matter. You just have to pick an angle. So basically what we have now is a polar representation of an angle and a distance. In such a representation, by doing just a little bit of math, you can basically see that the dot product of any point on the line xy, dotted with the cosine theta, sine theta location of this normal, is equal to d. There's a lot of ways to do it, but basically you can show that if you formulate it this way, that x cosine theta plus y sine theta equals d. So it's a lot. Not a lot. It's a little bit ugly. Well, it's beautiful if you like trigonometry. It's ugly if you like algebra. It's a little bit more ugly than the y equals mx plus b formulation, but it doesn't have this problem that any of our lines are ill-defined. This is a perfectly fine way of representing any line. You can have any direction you want. Theta can go however it wants to go, and you can go right through the origin. D can be 0, or it can get as big as you need it to go. One of the interesting things now is, if you take a look at this equation, if I know x and y, what I have left in terms of d and theta is a sinusoid, all right? Which is why we say that a point in image space is now a sinusoid in Hopf space, and we'll see an example of that in a minute. See, before we had this beautiful duality of a point in image space was a line in Hopf space, and a point in Hopf space was a line in image space. Well, because we've introduced this cosines and sines, it's still a duality, but it's no longer just simply between points and lines. One other comment about this. There's a redundancy or an ambiguity here. Let me draw it to you this way. Here's d. So if d can only be positive, this line has to be able to spin all the way around. So theta would have to go from 0 to 2 pi, 0 to 360 degrees. But if d could be positive or negative, then theta only has to go from 0 to pi, or 0 to minus pi, depending on how you draw that. The idea is you'd only need 180 degrees worth of coverage. Which way you do it doesn't really matter. In our algorithm, we'll do it in a particular way. But there's just this trade-off between, if you let d go positive to negative, positive and negative, then it only has to go 0 to pi. In fact, you can restrict things even more. If you make this be the origin of your image, the top left-hand corner, if you're going to say that your line has to be within the image, okay, then that restricts even more because it has to cut off that quadrant, so theta and d are restricted even more. But these are just choices that you make in terms of how you code up the algorithm. So speaking of the algorithm, let's take a look at it. So we're going to use the polar parameterization of the line, the polar representation, and something called a Hopf accumulator array, which is just the fancy word for the thing that's going to collect the votes. You're basically going to have an array, 2 dimensions in this case, where the bins represent different values of d and different values of theta. One of the things you'll have to decide, and by the way, you'll be implementing this, is how big are the bins? How many of them are there? So if it goes from 0 to, let's say, 0 to pi, well, if you have every 1 degree, then there'd be 180 bins. If you had every 10 degree, there'd only be 18. So you have to decide how big the bins are. So given this equation in the accumulator array, here is the algorithm. And I hope you appreciated that I tried to color code this. It looks garishly ugly, but it tries to keep everything clean. So the basic Hopf algorithm is this. You initialize your accumulator array to 0 everywhere. Then for every edge point, so we have to have a set of edge points. That is, at every place in xy, we have to know whether it's an edge point, or we have a list of them. Somehow, we know which points are edges. In fact, how do we know that? Because we did that last time, right? So you know how to do this in MATLAB or Octave, or you can write it in assembly code if you're really masochistic. So for each edge point xy, what we do is, so here I use theta from 0 to 180. That's, supposed to be 1 degree increments. All right. Solve for d. We just use that equation. Since we have x and y and we have theta, we can solve for d. But notice I'm not doing anything to restrict d being positive or negative here. So it could be positive, could be negative. And I have to then set h of d, comma theta I have to increment its vote. So if D is negative, what that means is, what I really mean is the bin of that D. So maybe my D goes from minus 100 to 100. So I would have 201 bins if I do them by steps of 1. So if I got a minus 20, I'd have to add 100, that'd be 80. You get what I'm saying, right? The D value goes into its bin. So the bin of that D value gets incremented by 1. After you've done all the voting, you find the values of D and theta where H of D of theta is a maximum. So you want to find these peaks. By the way,